Welcome to today's paper reading. Today's paper is titled PathMMU, a massive multimodal expert-level benchmark for understanding and reasoning in pathology. This paper was published on AR14 by Yuxuan Sun and colleagues from Zhejiang University and Westlake University. PathMMU is the largest and highest quality expert-validated pathology benchmark for large multimodal models, LMMs. It includes 33,428 multimodal multi-choice questions and 24,067 images. The construction of PathMMU leverages GPT-4V's capabilities, using over 30,000 image caption pairs to enrich captions and generate questions and answers. To ensure the benchmark's authority, 7 pathologists scrutinize each question under strict standards. This process sets an expert-level performance benchmark for PathMMU. Figure 1 provides an overview of the PathMMU benchmark, highlighting its construction from a diverse array of high-quality data sources. This benchmark includes 33,428 multimodal multi-choice questions in pathology, which are collaboratively crafted by AI and human pathology experts. Notably, even the most advanced large multimodal models, LMMs, significantly underperform when compared to human experts on the PathMMU, indicating the challenging nature of this benchmark. Pathology is crucial in modern medicine, providing the basis for diagnosing and understanding diseases. Techniques such as liquid-based cytology are vital for early detection, while biomarkers like HER2 and PD-L1 guide targeted therapies. The field has evolved with digital pathology and AI, shifting from traditional microscope use to AI-driven image analysis. This has led to the development of large multimodal models, LMMs, that offer general task-solving capabilities. To evaluate these models, PathMMU has been introduced, a benchmark comprising 33,428 QNAs and 24,067 images, annotated by experts to ensure high quality and relevance. The development of multimodal models has been significantly advanced by large language models such as BERT, GPT-3, T5, and Llama. These models have been integrated with vision models to create versatile multimodal models like CLIP, Flamingo, BLIP2, and Fuyu. In the realm of large multimodal model, LMM, benchmarks, datasets like LAM, LVLMEHub, and SEED have been crucial for evaluating model capabilities. In the medical field, datasets such as VQARAD, VQAMed, and PMCVQA have been instrumental in assessing AI capabilities in radiological diagnostics. Additionally, PathMMU has been developed as a high-quality, expert-verified pathology benchmark to address the limitations of existing datasets. Figure 2 presents a detailed comparison between PathMMU and other existing benchmarks in the pathology domain. The key aspects highlighted include the extensive and comprehensive sourcing of Q&A pairs in PathMMU, which undergo rigorous multi-tiered filtering processes. This involves initial filtering by multiple large language models, LLMs, and subsequent strict reviews conducted by professional pathologists. Furthermore, each question in PathMMU is accompanied by a detailed explanation, enhancing the dataset's quality and professional curation. These features collectively position PathMMU as the most comprehensive and highest quality large-scale pathology dataset currently available. The PathMMU benchmark is designed with 5 key principles to ensure its effectiveness and relevance. Firstly, it includes comprehensive and specialized data from various authoritative sources such as PubMed, pathology textbooks, and social media posts by pathologists. This data is reviewed by 7 human experts to maintain professional standards. Secondly, the questions are crafted to require detailed observation of pathology images, ensuring they are not solvable through simple textual interpretation. The dataset is also large-scale, currently the largest in pathology, allowing for thorough exploration of LMMs. Additionally, high-quality images with clear details are prioritized, and explainable answer choices are provided to enhance model interpretability. The construction of PathMMU involves a meticulous 3-step data processing and generation protocol. This includes data collection from diverse sources, detailed description generation using GPT-4V, and question generation followed by expert validation to ensure the questions are effective and aligned with professional pathology standards. Figure 3 provides a comprehensive overview of the three primary processes involved in the generation of Q&A pairs for the PathMMU benchmark. The first process is data collection and preprocessing, which involves gathering data from diverse authoritative sources such as PubMed, YouTube, Twitter, and Pathology textbooks. This step ensures a wide range of high-quality image-text pairs are integrated into the PathMMU framework. The second process is detailed pathology image description generation, where GPT-4v is prompted to focus on describing the morphology of cells and tissues, enhancing the relevance and precision of the descriptions. The third process is question generation with LLMs filtering and expert validation. Here, GPT-4v creates multiple-choice questions based on the image descriptions, and these questions undergo a filtering process using multiple LLMs to ensure they cannot be answered through educated guesses alone. Finally, expert pathologists validate the questions to ensure they meet professional standards, resulting in a robust and reliable dataset for evaluating pathology LMMs. In this section, we present the experimental evaluation of PathMMU. We first discussed the zero-shot evaluation of large multimodal models, LMMs, where 14 open-source and 4 closed-source models were tested, with 15 models showing an accuracy below 40%. Next, we examined the robustness of these models to image corruptions, finding that while they demonstrate robustness, their performance significantly drops when images are replaced with Gaussian noise, indicating a reliance on textual information. Finally, we report the results of fine-tuning these models, which show a significant improvement in performance, particularly when fine-tuned for direct answer generation, bringing the models closer to expert-level proficiency. Figure 4 presents an illustration of corrupted pathology images on the left, showcasing various types of image degradation. On the right, the figure displays the performance of large multimodal models, LMMs, across different levels of color-related corruptions, brightness, hue, saturation, and image quality-related corruptions, pixelation, JPEG compression, bubble blur, motion blur, defocus blur. The severity levels range from 0, uncorrupted images, to higher levels representing increasing degrees of corruption. This analysis helps in understanding the robustness of LMMs in handling real-world image quality variations, which is crucial for their application in pathology diagnostics. Figure 5 presents a detailed analysis of the performance of various large language models, LLMs, compared to human experts in guessing answers from text-only samples. The left panel shows the performance on 100 filtered samples, where LLMs significantly outperform human experts. The right panel expands this analysis to 1,600 samples, introducing a method where original questions are randomly replaced with others from the dataset while keeping the options unchanged. This experiment aims to validate the source of LLM's guessing ability. Additionally, the use of BERT series models, specifically through their next sentence prediction, NSP, capability, is employed to assess whether an option is the sequential sentence following a question. This approach further supports the hypothesis that LLMs can effectively guess answers based on textual patterns and common options, demonstrating their proficiency in identifying potential shortcuts within the questions. Table 1 presents the comprehensive results of various models on the PathMMU validation and test sets. The table not only showcases the performance of large multimodal models, LMMs, but also includes baselines for large language models, LLMs, that only process text inputs. The best-performing LMM in each subset is highlighted in bold, while the top-performing LLM is underlined. This comparison provides valuable insights into the effectiveness of multimodal versus text-only approaches in handling pathology image data. Table 2 evaluates the robustness of models on the PathMMU test tiny set, highlighting performance changes with corrupted images. The table uses green to indicate improvements and red to signify degradations compared to the model's performance with uncorrupted images. It provides detailed metrics across various types of image corruptions, such as brightness, hue, saturation, pixelation, JPEG compression, and blur effects. This evaluation helps in understanding how well models maintain their accuracy under different levels of image quality degradation. Table 3 presents the results of large multimodal models, LMMs, tested on the PathMMU dataset with original images replaced by random Gaussian noise images. The table shows a significant performance drop across all datasets, indicating the model's sensitivity to image corruption. Notably, LLVA 1.5-13b exhibits the highest degradation in performance, suggesting that larger models may be more adversely affected by such noise. This data underscores the need for robust models that can maintain accuracy even when image quality is compromised. Table 4 presents the results of large multimodal models, LMMs, on the PathMMU test set after fine-tuning. The models, InstructBlip FLAN T5XL and InstructBlip FLAN T5XXL, were fine-tuned to either output the answer directly, W/A, or to output the answer along with an explanation for the answer, W/ANE. The results show significant improvements in performance after fine-tuning, with the models achieving notable increases in accuracy. Notably, these fine-tuned models outperformed the current leading model, GPT-4v, demonstrating their effectiveness in pathology image analysis tasks. This table highlights the substantial benefits of fine-tuning LMMs on specialized datasets like PathMMU, which enhances their capabilities in interpreting and reasoning with pathology images. In this study, the authors introduced PathMMU, the largest and highest quality pathology benchmark to date. This benchmark was meticulously constructed through a rigorous data collection and curation process, which included a strict manual review by 7 professional pathologists. The authors also established a human expert performance benchmark to quantify the gap between advanced large multimodal models, LMMs, and human experts. Experimental results show that LMMs significantly lag behind human experts on PathMMU, often failing to observe details in pathology images and sometimes neglecting visual information. However, after fine-tuning on PathMMU, LMMs showed notable performance improvements, even surpassing GPT-4v. Despite not achieving human expert-level performance, these models demonstrate promising potential for analyzing pathology images. Looking ahead, the authors identify several key areas for future development of LMMs in pathology, including the need for better integration of visual and textual modalities, the development of interpretable models, and the capability to handle multi-image inputs. The authors believe that PathMMU will catalyze significant advancements in the development of next-generation LMMs in the pathology field. Thank you for watching.